In the first video, we were introduced to the concept of refraction and Snell's law and this formula. And I told you that I would begin in the second video here to explain bit by bit these individual items in the formula. Okay, so what does all this stuff in the formula mean? Well, we'll start with the I's and the R's. The I's stand for incident, the R's for refracted. And remember, incident is the one coming into, and refracted is the one that's bent. Okay, now the N. The variable N stands for something called the refractive index. Now in this equation, there's two N's. There's an N of incidence and an N of refraction. Now, we're going to talk right now about the refractive index and what is it. Now, each material, each medium that refracts light, that light can go through and be refracted by, has a different refractive index, which is a number that we give to it based on how fast light travels through it. Because the speed of light through the material helps to determine how that material is going to bend the light. Okay, in determining the refractive index, the scale, what numbers to give what materials, we start out with number 1 given to the speed of light in a vacuum, because the speed of light in a vacuum is the fastest thing that we currently know of. And that speed is approximately 3 times 10 to the 8th meters per second, or 3 times 10 to the 10th centimeters per second, or 186,000 miles per second, approximately. Those are approximations. And the next material is air. Now, with a vacuum, there is no substance in a vacuum, so there's nothing to slow the light down. In air, there is some substance to air, so there is a little bit of density, there is something to slow the light rays down. However, it's so small that we actually use the same refractive index for air. I believe the correct refractive index is 1.0002, I think, I'm not even sure. But we use 1 for air and a vacuum. So from here on out, I'm probably going to say the speed of light in air rather than the speed of light in a vacuum. All other materials, all other substances, all other mediums is the best word. All other mediums that light can travel through derive their refractive index by how fast light travels through them compared to how fast it travels through a vacuum or air. I'm going to say that again. The refractive index of a medium describes how fast light travels through it compared to how fast it travels through air. And here's a formula that describes that in a very simple way. N is the variable we use for refractive index. N equals the speed of light in air, and remember, technically it's the speed of light in a vacuum, but the speed of light in air divided by the speed of light in that particular medium. That will give you the refractive index of that medium. Okay, back to Snell's law. Now we know what the variable N means. N is the refractive index of the substance. And N sub I would be the refractive index of the substance that the incident ray is in. That means the initial ray. And N sub R would be the substance that the refracted ray is in, the substance that refracted the light. Okay, now in order to further explain some properties of this, I'm going to create some nonsensical scenarios, okay? Light travels through any medium really, 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 really fast, okay? I'm going to pick some dummy numbers that really aren't going to make any sense in the real world, but it'll help explain it to you in a simpler terms, okay? So just bear with me while I do this. Okay, let's just say that light traveling through air travels at 10 miles an hour, and then it hits a second substance, a transparent medium, and through that second medium, it travels at 5 miles an hour. What's the refractive index of the second medium? Well, according to our formula, we would take the speed of light in a vacuum or the speed of light in air, divide it by the speed of light in that second medium, and we would come out with our refractive index for that medium. That medium, of course, would have a refractive index of 2. Now let's just say we have another medium now, and light travels through that medium at 2 miles an hour. What's the refractive index of that medium? Well, that, of course, will equal 5. Okay, so why am I doing all this? Well, I want you to look at the patterns and the relationships here, because I know I picked ridiculous numbers and ridiculous speeds, but the patterns will hold true regardless of the numbers. Okay, notice how 5 miles an hour is faster than 2 miles an hour, yet 5 miles an hour yields a refractive index that is lower than the slower material, the slower medium. We can conclude, and we would be correct, that the slower the speed of light through the medium, the higher the refractive index is going to be. Okay, next, and this is just common sense, what would make the speed slower? Okay, I said the fastest thing that we know of is the speed of light in a vacuum, and I said that's because there is no substance in a vacuum to slow it down. So basically, the more substance, the denser, the slower it's going to be. Think of this, if you're walking through air, there's not a lot to slow you down, so you can walk pretty fast. But if you were to walk through water, there's a lot more, it's denser, there's a lot more to slow you down, so you have to walk slower even though you're putting forth the same effort. Now, if that water, that pool that you're walking through is all of a sudden jello, that's going to slow you down even more because it's even denser. So slower speed, denser material, higher index of refraction. That's kind of a relationship you might want to memorize. Okay, so we're working through this formula, and we've got down the I's, we've got down the R's, and we've got down the N's. So next video, we are going to go over sine of angle I and sine of angle R and try to put this all together. So hopefully you'll watch the next video, which would be number 3 in this series. Thanks for watching.